Let's look at this example here. The real plane, R2, is also a vector space. Now we're not going to check all of them, but under the usual meaning of addition and multiplication, scalar multiplication, we can show by going through those 10 conditions that it is indeed a vector space. But we'll just check the first, let's just check two conditions. We're going to check the closure conditions for one. So if we look at this, right? So if we add two vectors, oops. Well, since we're dealing with R2, we're dealing with real numbers here. There's no restrictions on these numbers like there was in the previous example. So if we do vector addition, what do we get? We get another vector where we are adding component-wise. And of course, when we add two real numbers, we get another real number. And so we get a vector whose components are real numbers, and therefore we get a vector that is still in the plane, the real plane. Now what about scalar multiplication? Well, if we take r times xy, where x and y are real numbers, then we're going to get another vector where we're multiplying by a scalar times, which is a real number, times another real number. And of course we get another vector that is also a member of R2. And we can find, again, the other 8 conditions also satisfied. And in fact, we could do this for all, we can do this for all r to the n. So for each r to the n, we can do the same way in a similar way, show that they're vector spaces under the usual operations of vector addition and scalar multiplication. Now in the case where we have R1, right, that's just the real numbers. R1, we don't typically write them as column vectors, right? We just write them as numbers, but still, it's satisfied there. Now, I think that's it. Okay, we'll go on to the next example and we'll look at some subsets.